Hello, welcome to another module in this massive open online course. We are looking at the mathematical preliminaries for optimization. Let us continue our discussion with another concept, namely an inner product space. Okay. So, we want to start looking at the concept of what is known as an inner product space. Now, what is an inner product space? Now, an inner product space of a real vector. Now, the inner product of a real vector space the inner product of a real vector space is an assignment of a real number and for any two vectors u bar v bar, that is denoted by this notation u bar, the inner product of u bar comma v bar, and this is defined for any two vectors u bar v bar, in this case real vectors. For any two vectors u bar comma v bar, and this is the inner product, which is a real number in the case of a real vector space, and which satisfies, the inner product satisfies the following properties. The inner product of the vector satisfies the following properties. First property is linearity, which is AU bar plus, that is the inner product of a linear combination AU bar plus BV bar is the linear combination of the inner products, that is, this is A times U bar, inner product of U bar W bar, plus B times the inner product of V bar comma W bar. Okay. So, this basically is the linearity property. That is the inner product of the linear combination A U bar plus B V bar with the vector W bar is the linear combination of the inner products A times the inner product U bar with W bar plus B times the inner product of V bar comma W bar. Okay. This is the first property. Then we have the symmetric property or the symmetry. Which is very simple, that is the inner product of U bar V bar equals the inner product of V bar comma U bar. Then we have, so if you call this property number 1 linearity to symmetry, then we have the positive semi definite property. The positive semi definite property, it must be the case that for any u bar, that is for any u bar element of the vector space V, then the inner product of u bar with itself must be greater than or equal to 0, and more importantly, and also u bar, the inner product with itself equals 0 if and only if u bar is itself 0. So, inner product is 0 if and only if the vector u bar is 0. So, these are this is the definition. It is an assignment of a real number for a real vector space and satisfies the linearity, symmetry and the positive semi definite properties. Okay. Let us look at a simple example to understand this. For instance, the standard product, let us consider the standard dot product between two vectors. All right. Consider two vectors. The dot product is defined for between two vectors. Consider u bar equals u1 u2 up to un and v bar equals v1 v2 up to vn. Then now these are real vectors, n dimensional vectors. That is, you can say that belong to the space of n dimensional real vectors denoted by this bold r to n, and is also termed as the Euclidean n space. This is also termed as the Euclidean n space, and the inner product in this Euclidean n space between vectors u bar and v bar is defined as u bar transpose v bar, which is basically, if you look at this, that is u1 u2 un row vector times the column vector v1 v2 vn, which is basically u1 v1 un vn. Okay. So, this is the definition of the dot product. Okay. So, this is the dot product between two n dimensional real vectors, something that you might have well seen in your vector space or vector calculus class in high school. All right. This is a standard dot product, which is also denoted by the dot operator, that is u bar dot v bar. Okay. This is the dot product between two vectors. In fact, more specifically two real n dimensional vectors. Now, we will show that dot product is an inner product. Now that is very simple to see. First let us look at the linearity property. If you look at AU bar plus BV bar dot product with W bar, that is simply AU bar plus BV bar transpose times W bar, as we have seen, that is the definition of the dot product, which is A times U bar transpose W bar plus B times V bar transpose W bar, which is A times the inner product of U bar with W bar plus B times the inner product of V bar with W bar. Okay, so it satisfies the linearity property. Now coming to the symmetry property, we have U bar dot product V bar, which is equal to U bar transpose V bar, which is basically V bar same as V bar transpose U bar, which is V1 U1 plus V2 U2 plus Vn Un, which is V bar U bar, and 3, so its symmetry satisfies the symmetry property. Now we have to look at the positive semi definiteness. Now positive semi definite property, now you can see that the inner product of U bar with itself is U bar transpose U bar, which is U1 square plus U2 square plus Un square, which is greater than or equal to 0. Further, in fact, we have seen this is nothing but this is used to define the 2 norm square, that is, this is the L2 norm square, norm U bar square, which is greater than or equal to 0. In fact, equal to 0 if and only if sum of the squares is 0, which means each of the components is 0, U1 equals U2 equals U of n equals 0, which means U bar equals 0. So, it is positive semi definite, that is U bar, inner product of U bar with itself is always greater than or equal to 0, it is 0 only when U bar, the vector, is identically 0, alright. And therefore, the standard, the dot product is an inner product and in fact this is also termed as the standard inner product. This is also termed as the standard inner product on Rn, that is the Euclidean n space or the n dimensional set of n dimensional space of real vectors. Euclidean n space or the n dimensional space of real vectors. The dot product is an inner product. Let us now consider another example for 2 dimensional vectors. Instance, we have x bar equals x1 x2 and y bar equals y1 y2. So, both of these are basically 2D vectors, that is they belong to the 2-dimensional Euclidean space. And let us define this assignment x bar y bar for this 2D vectors as twice x1 y1 minus x1 y2 minus x2 y1 plus 5 x2 y2. Now, what we want to do is we want to show that this is an inner product. This is a valid, this assignment is a valid inner product, and this can be shown as follows. As usual, we start with the linearity property. Now, let us consider a vector that is Ax bar plus Bx tilde, that is A times x1 x2 the 2-dimensional vector plus B times x1 tilde x2 tilde. Alright. So, we are taking a linear combination of the two vectors x bar and x tilde. Now, for this to be an inner product, let us consider now A x bar plus B x tilde, the inner product with any vector y bar. Now, this can be shown as, now we can see this is equal to twice x1 plus B x1 tilde into y1 minus x1 plus Bx1 tilde into y2 minus x2 plus Bx2 tilde into y1 plus 5 times x2 plus Bx2 tilde into y2. And now you can clearly see this is linear, that is, this can be written as A. If you separate the components and write it, you can easily see that this is A times x bar comma y bar plus B times x tilde comma y bar, and therefore, it is linear. Okay. So, satisfies, implies that this is linear. Okay. All right. So, we have shown that the assignment is linear. Now, let us know symmetry, the symmetric property, and this can be shown as follows. So, coming now to the aspect of symmetry, you can see that x bar y bar, this is equal to twice x1 y1 minus x1 y2 minus x2 y1 or minus y2 x1, I am sorry, minus x2 y1 minus x2 y1 plus 5 x2 y2. Okay. And now, this can also be written as, without any effort, you can see this is twice x y1 x1, interchanging the terms, the second and third term, this will be minus y1 x2 minus x1 y2 plus 5 y2 x2, and you can readily see that x1 y2 I will write as minus y2 x1, and you can readily see that this is nothing but the assignment y bar comma x bar. So, we have x bar y bar equals y bar comma x bar, and hence this implies that it satisfies the symmetry property. And finally, now coming to the positive semi definite property. Coming now to the positive semi definite property. Now, if you look at x bar, that will be twice x1 square minus 2 x1 x2 plus 5 x2 square, which is equal to, now I can write this as the sum of two terms, x1 square plus x2 square plus 2 x1 x2 plus x1 square plus 4 x2 square minus 4 x1 x2, and this is equal to, well, x1 plus x2 whole square plus x1 minus 2 x2 square, which is greater than or equal to 0. So, sum of two perfect squares, this is greater than or equal to 0. So, implies this satisfies the positive semi definite property. This satisfies the PSD property, and in fact, you can see this is equal to 0 only when it is equal to 0 only if x1 plus x2 both must be 0, because it is sum of perfect squares. So, both must be 0, x1 minus 2 x2 must also be 0, and this implies that x1 equals x2 equals 0. So, it is only 0 when x1 equal to x2 equal to 0, that implies x bar equals. So, we have the PSD property, which is x bar the assignment is greater than or equal to 0 and equal to 0 only if x bar equal to 0, that is what we have shown. Therefore, it also satisfies the PSD property, hence because it satisfies the linearity, symmetry and PSD properties, this is an valid inner product. All right. So, finally, what we have is that x bar comma y bar equals 2x1 y1 minus x1 y2 minus x2 y1 plus 5 x2 y2. We can now claim that this is a and this is not a coincidence. In fact, such an inner product can be constructed by observing the following thing. I can write this thing as this is equal to x1 x2 twice minus 2 minus 1 comma 5 y1 y2, which is nothing but x bar transpose A y bar, where A is this matrix. You have A is the matrix 2 cross 2 matrix, which is given as 2 minus 1 5. You can see that this is nothing but identical to the, this is basically another way of writing the inner product that we have just defined. And now you can show a very interesting property of this matrix. In fact, this matrix A is a positive semi-definite, positive definite matrix, alright. So, you can see that this matrix A is a positive definite matrix. And you can see this as follows. Remember, we said this matrix is, first see that this matrix is symmetric. We have A equals A transpose. Further, if you look at the eigenvalues A minus, that is, if you set the determinant of A minus lambda equal to 0, then what we have is you have the determinant of 2 minus lambda minus 1, 5 minus lambda equal to 0. This implies 2 minus lambda into 5 minus lambda plus 1 equal to 0. This implies, now if you simplify this, lambda square minus 7 lambda, I am sorry, this determinant is minus 1 minus lambda square minus 7 lambda plus 10 minus 1 equal to 0, implies lambda square minus 7 lambda plus 9 equal to 0, implies lambda equals, well, 7 plus or minus square root of 7 square 49 minus 4 into 9 36, 7 plus or minus 13 divided square root of 13 divided by 2, and you can see both the eigenvalues are greater than 0. Alright, it has two eigenvalues and the eigenvalues are strictly greater than 0. So, symmetric plus the eigenvalues greater than 0 implies A is positive definite. Okay, so A is a positive definite matrix. So, A is a positive definite matrix, and therefore, hence X bar transpose. So, now in fact an interesting property, and you can easily show this, that is, if you look at two vector, if you define an inner product, that X bar between X bar and Y bar as X bar transpose A Y bar, where A is positive definite, this is a inner product, that is, this is an this is a inner product where A is a symmetric positive. Let me also just write this, A is a, where A is an inner product. This is an inner product, X bar transpose A Y bar, where A is a symmetric positive definite matrix, is an inner product. Alright. And one of the other interesting aspects of the inner product is that it can also be used to define a norm, and that is one of the most interesting and important aspects of the inner product. It induces a norm, and that norm is given as follows. So, the norm is, so inner product can be used to define a norm. So, the norm can be defined using this concept of inner product, and in fact it can be defined as follows. We have norm of u bar square, this is equal to the inner product of u bar with itself, which means basically the norm of a vector u bar is equal to square root of the inner product of u bar with itself. And in fact, the unit norm vector can now be defined as u hat equals u bar divided by norm of u bar, that is u bar divided by square root of u bar. And in fact, what we have seen is, and this process is also termed as normalization, that is when you divide a vector by its norm, you can also say that the vector is normalized. And you can also see this is true for the standard inner product, that is the standard inner product on Rn, that is if you look at x bar comma x bar, where x bar belongs to Rn, and this is the standard inner product. We have already seen that inner product of x bar with itself is basically, this is x1 square plus x2 square plus xn square, which is nothing but the L2 norm square. Okay. And therefore, this is the square of the norm, and we have already seen this for the standard inner product. What this result says is that not just for the standard inner product, which is given by the dot product of two vectors, but any inner product on these two vectors x bar y bar can be used to define a norm, that is the norm is given as the square root of the inner product of x bar with itself. Okay. For instance, in the previous example we have seen x bar transpose a y bar, alright, which means the norm of x bar under that inner product is given as square root of x bar transpose a x bar. Okay. So, the norm of x bar is equal to square root of x bar transpose a x bar, and this is for the previous example. Okay. Let us look at other examples of inner products. So, we have some other examples of, we have already seen u bar transpose v bar, that is the standard norm on Rn, this is an inner product, this we have already seen. Now, another interesting application of inner product is, let us consider the space of continuous functions on an interval a comma b denoted by C of a comma b, that is the set of continuous functions on a comma b on interval a comma b, and let us say we have two functions f comma g which belong to C of a comma b, that is their continuous functions on the interval a comma b. Then the assignment defined as f of g equals integral over the interval a comma b f of x g of x, or f t dt, that is this integral f of x g of x dx, this is an inner product. In fact, this is a very interesting application, and in fact this can now be used to define a norm. So, this is an inner product for functions f comma g, and in fact the norm that arises is basically nothing but norm of f is integral a comma b, or norm of f square is basically inner product of f with itself, that is integral of a comma b, integral on the interval a comma b f square x dx, or this is nothing but the energy of the signal. That is, if you look at this as a signal in time, if I think of this as a signal in time, this is basically the energy of the signal in interval this is the energy of the signal in the interval a comma b. All right. So, that is another. So, it can also be used. So, basically one can also define an inner product, correct. One can also define an inner product on the space of continuous functions, all right, and therefore define the norm or the norm and as well as the norm square. In fact, the norm square of the function is based, or the signal is the energy of the signal in that particular interval. Another interesting example of this inner product space, consider the space of M cross N matrices. So, we have the space of M cross N matrices, example M equal to 3, N equal to 2 implies we have 3 cross 2 matrices, and for instance the 3 cross 2 matrices are A equals A11, A12, A21, A22, A31, A32, and we have B, the matrix B equals B11, B12, B21, B22, B31, B32, and the inner product AB defined as trace of B transpose A, that is the, now this is an interesting concept, that is trace of a square matrix. This is the trace of a square matrix, the trace operator. This is defined as equal to sum of the diagonal elements of a square matrix. Sum of the diagonal elements of a square matrix, that is the trace of the square matrix, and this can be shown to be an inner product. This can also be shown to be an inner product. Trace of this can also be shown to be an inner product. All right. So, what we have done in this module is we have looked at the inner product, its definition, the various properties, or when is an assignment an inner product, and several examples. We will continue this discussion in the next module. Thank you very much.